Hello and welcome back to session 3 of statistics using R, where we deal with managerial statistics concepts using the R language. This is the third session. In the previous session, we had talked about the normal distribution and we had defined the central limit theorem. Now we will see the central limit theorem in action. So just to recap, what is the central limit theorem? It is a very important and kind of a cornerstone theory in statistics, which states that irrespective of the population distribution, if we take large enough samples, by large enough we mean if we take sample of size greater than 30, greater than or equal to 30, then the distribution of the sample means would be a normal distribution, right? So if we take 1,000 samples from a population and if we compute the means of each of those 1,000 samples and we plot the frequency distribution of those means, then the resultant distribution that we will get is a uh, normal distribution. Why is this important? It is important because it helps us to approximate the population characteristics from a sample, and it allows us to use assumptions of normality and certain formulas which are easily applicable to normal distributions, even when the population is not normally distributed. So, just to make the concept crystal clear, we will look at an example, right? So again, set.seed 123 does not really matter. It just because we'll be generating certain random numbers. For the purpose of giving the example, we are setting the seed to something. It could be 123, it could be 1, 2, 3, 4, 5, 6. Does not really matter, right? We are creating a population here. Population, I'm using the function called R exponential. So I'm creating basically an exponential distribution, right? Which is very different from a normal distribution. So, if we have to see the histogram of this population that we have created, it is an exponential distribution, right? It reduces exponentially, as you can see. It is very different from a normal distribution, which we have seen in session 2, right? This is a population, it contains 10,000 values, and it is very different from a normal distribution, right? It's not normally distributed. So now what we will do is we will basically look at three scenarios, right? The first scenario is where we are taking up 1,000 samples. Each sample is of size 10 from the population, right? So each sample is basically small sample, right? It does not conform to the uh, central limit theorem requirements of the sample size of being at least 30. So what we're taking is that we're taking 1,000 samples. So we are taking 1,000 samples, each of size 10, and we are computing the means of each of those 1,000 samples. So we will take that, right? In the subsequent step, we are increasing the sample size to 30 and then to 100. Okay. So what does these variables now contain, right? So let us quickly see sample means 10, for example. What does it contain? So it contains, so it is again a list. It has 1,000 values and it contains certain values inside of it. It means that it has taken 1,000 samples and computed the mean of each of those 1,000 samples, stored it in the form of a list, right? Similarly for 30, similarly for 100. Now, uh, when we created the population, we can just look at the mean of the population, right? Using the concepts that we studied in session 1. So the mean of the population is coming out to be 1.006, right? Now we can also similarly take the means of each of the scenarios that we have computed above. So sample size of size 10, 30, and 100, right? So we can see that the means in all of these cases is pretty similar to the original population mean of 1.006, right? So that is basically, another, uh, concepts of the central limit theorem, which states that the mean of the sample means would be close to the population mean. The mean of the sample means would be close to the population mean. So that is the concept here, right? Again, we can just plot these three scenarios, the sample mean 10, 30, and 100 to see what has happened, right? We can take a histogram. So when the sample size is 10, we see that the distribution is kind of looking like a normal distribution, but it is not so much normal, right? There is a bigger tail on the right side, for example, and all that. And this is happening because the sample size is lesser than what is statistically required for central limit theorem, right? So even though it is close, it is not very good normal distribution. When we look at the same thing for sample size of 30, we see that it much better approximates a normal distribution, right? That is because the sample size is now increased, and hence we see a better distribution and better looking distribution here. And when we go to the sample size of 100, it becomes even better, right? So it becomes more of a normal distribution here as well. So actually, with sample size of 30 in our example, it was more or less looking like a normal distribution, better normal distribution than what it is here. But even so, both of these are approximating normal distribution better than the sample size of 10, right? This graph also looks a little bit flatter as compared to the sample size of 30, right? And that is also one of the differences. So, hope the concept of central limit theorem is now clear. We do not need to use central limit theorem as it is in most cases, but it acts as the underpinnings of multiple other theories as well. So, hope this was helpful. Please stay tuned for the next part.